Today, we will be exploring the topic of ionization energy. Ionization energy is defined as the amount of energy to remove an electron from an atom or molecule. By removing an electron, the atom or molecule becomes positively charged, which makes it a cation. Therefore, ionization energy can also be referred to as cationization energy. Some elements can have several ionization energies referred to as first ionization energy, second ionization energy, and so on. The first ionization energy is the energy required to remove the outermost highest energy electrons, and the second ionization energy is the energy required to remove any subsequent high energy electrons from the cation. And it continues from there. Coulomb's law is helpful when trying to understand most quantitative and qualitative characteristics of elements on the periodic table. I've included the equation of Coulomb's law in the PowerPoint. Coulomb's law describes the relation between the electrical force of two charges and the quantity of the charge on the objects. According to Coulomb's law, we expect electrons closer to the nucleus to have a lower potential energy, which require more energy to remove from the atom. Non-valence electron clouds act as electron shields which reduce the nuclear charge felt by valence electrons. Before exploring ionization energy, it's helpful to understand how the trend of atomic radius works across the periodic table. So as you can observe from the picture, atomic radius decreases from left to right. This is because as you go across a period or down a column, the atomic number is increasing. As the atomic number increases, both the protons and electrons increase by the same number. The electrons are added to the valence shell, while the protons are added to the nucleus. The protons contribute to a greater nuclear charge in the nucleus. Because electron shielding from electrons that are not in the valence shell remain constant, because their number is not changing, the nuclear charge increases, which results in a stronger force to attract the most outer electron shell. So as a whole, as you go down the period or down the column, atoms will become smaller in size. Ionization energy can also be understood to correspond to atomic radius trend, which is why the concept was explained before. As electrons are brought closer to the nucleus across a period, more energy is required to remove them. When we look at the periodic table that reflects the trend of ionization energy, we can observe that the directionality of increasing ionization energy is opposite to the trend of increasing atomic radius. Here is an example of an ionization energy versus atomic number graph. Each maximum of the graph with a labeled element represents a noble gas, the last group found on the periodic table. After each noble gas, a new period starts. So when we look at helium, lithium comes after, then beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then another noble gas. After argon, the distance between the noble gases increases. This is because of the elements on the periodic table increasing in the period of group 4 and after. We learned before that the general trend of ionization energy increases from the bottom left to the top right. However, there are exceptions that do not follow the expectation to increase as observed on the graph between each noble gas. Interpreting the part of the graph that is between helium and neon, we can see that both boron and oxygen decrease in ionization energy after the preceding element. We will explore further why this occurs. One thing that must be understood is that atoms are always trying to be stable. Atoms are most stable when their valence shell is half filled or full completely. To understand the reason behind exceptions to the periodic ionization energy trend, it is important to understand the relationship between energy and stability. Stability is a low state of energy. For example, a ball at the top of a slide is less stable than a ball that is at the bottom of a slide. If it is on the bottom, it will just sit there and do nothing. If it's at the top, it could roll down. In the same understanding, when an atom is stable, it has a lower energy than an unstable atom. If a stable atom becomes unstable, it must absorb the energy from somewhere else. If an unstable atom becomes stable, it must release energy. So we know that nitrogen precedes oxygen on the periodic table. We also know that the ionization energy trend increases from left to right. So we would expect oxygen to have a higher ionization energy than nitrogen. But we know this is untrue because we just found out that oxygen is one of the exceptions on the periodic trend. So we're going to investigate, why does oxygen have a lower ionization energy than nitrogen? The first thing that we'll do is write out the electron configuration for nitrogen before losing an electron. After removing an electron, we notice that it has moved from its stable state to a half-filled shell to an unstable state. So it's moving from a 2p3 to a 2p2. And then we remember, when a stable atom loses an electron to become unstable, it releases energy. So it would increase the amount of ionization energy that is recorded. The next thing that we can do to compare is draw out the electron configuration for oxygen. After the ground state configuration is drawn, we can also draw the electron configuration after an electron is removed. So, after the configuration is removed, we see that it has moved from a 2p4 orbital to a 2p3. So, an unstable atom has now become stable. And we remember previously covered that when this happens, energy is absorbed. So, in the process of removing an electron from the pull of the nucleus costs energy. Even though this happens, we get a small of energy back, which makes up for the difference in ionization energy between nitrogen and oxygen, which is why oxygen has a lower ionization energy than nitrogen.